Good morning.
Good morning.
Oh, I love it. Thank you. Oh, it's so much fun to be back here. First came to Japan 5 years ago now, and loved it then and love it now. In fact, we've actually done business with Rakuten. My son, when he turned 18, one of the presents we said was, you can go anywhere in the world you want to go, we'll take it. And he said, I want to go to Tokyo. So he and I came to Tokyo for a week, and he fell in love with the vending machines, and he fell in love with milk tea. So we get back to Dallas, and of course you cannot get milk tea in Dallas. And so my wife went online and ordered a case of milk tea from you guys. And it was delivered, which was fantastic. So, why am I here? I know that a lot of you, how many people here are Ruby programmers? Oh, okay, so most of you are probably Ruby programmers. Me too, I'm a Ruby programmer. I love Ruby. I have some proof. I've written 4 versions of a book on Ruby. I love Ruby. I've written 4 versions of a book on Rails. I love Ruby. Our online site, it's an e-commerce site. I can teach you guys a thing or two about e-commerce. But this is our site. It is in Ruby. It's 110,000 lines of Ruby, most of which I wrote initially. So, I love Ruby. I think I can say that. But, and there's always a but, I also love programming languages, programming in general, and I have this I like bright, shiny, new things problem. I discovered Ruby because I love programming languages. And this was back 15 years ago. And back then, I would go out and I would look for programming languages, maybe 1 or 2 a week, and I would try them. And Ruby was different because I tried Ruby and I kept using it. I really did fall in love that first day. And I've been using Ruby since then. But that hasn't stopped me trying new languages. I try them all the time. And the reason for that is what I really like doing is getting things done. What I really like doing is delivering to my customers. Right? There's nothing better than getting something and seeing people use it. So I look for tools that let me do that. And programming languages are really just tools. I get very nervous when I say to somebody, what do you do? And they say, I'm a Java programmer, or I'm a C programmer, or I'm a Ruby programmer. Because really that's very, very constrained. Right? If you're a Java programmer, if you think of yourself as a Java programmer, then every solution to any problem is going to be a Java program. And that's not the way to think about things. Instead, you should be saying, what is the best solution I can deliver here? Quite often, the best solution is no program at all. But I think we have to keep our minds open, and we have to look for different tools. And I came across Elixir first about 2 years ago, and I can't remember why. I played with it, and I wasn't that impressed. And then at the beginning of this year, I was talking to a friend, a man called Corey Haynes, and I said, I'm looking for that language that's going to make me excited again. I'm looking for a language where I can show people what functional programming looks like. And he said, you should look at Elixir. So I went back, we were in a hotel, so I went back to my room, and I downloaded Elixir at about 8 o'clock at night, and I was still playing with it at 2 o'clock in the morning. It was really, really good. And so I'm going to talk about why I like Elixir. So, Moore's Law. Wouldn't it be cool if Moore's Law was named after Roger Moore? I mean, that would just be so good, but it's not. It's named after Gordon Moore. Better smile, doesn't have a gun. And Moore's law is one of the reasons that I'm excited about Elixir. The original Moore's law says that the complexity of the most economic integrated circuit doubles every year. A year later, he realized he was being a bit optimistic, and he changed it to say every 2 years. But the amazing thing is, he made that prediction back in the 1960s, and it has held ever since. So the first computer I ever wrote code for, I think, was an 8008, way back there. So that probably had, what, 3,000 to 4,000 transistors on it? And I've used quite a few of those machines between now and then. This particular laptop here is there on this graph, which, when I found that out, was staggering, because it has roughly 1 billion transistors in its CPU. My son just put together a gaming computer, and it has the same processor, so he's got 1 billion transistors in his processor. He's got 4.3 billion transistors in his graphics card. I mean, that to me, maybe I'm just old, but to me, the idea of 5.3 billion transistors, you know, just so he can play Call of Duty, that's just like ridiculous, you know, absolutely ridiculous. So, just how much is 1 billion transistors? Well, somebody took apart a MacBook Air and they measured the processor. It's 121 square millimeters, which means that I've got 8.26 million transistors on every square millimeter. Or to put it another way, roughly 2,000 times more transistors per square millimeter than I had on the first computer I ever programmed. How big is a square millimeter? Well, I finally found a use for this paperclip man. If you take a paperclip and cut across it, that's roughly a square millimeter. So 8.26 million transistors. Now, that's a fantastic number. Wouldn't it be nice if that just meant that every year our programs could run twice as fast or do twice as much? But the problem is they can't. And they can't because the architecture of the machines is limited. It's limited by things like the speed of light. It's limited by things like quantum tunneling. You physically cannot have 4 billion transistors all working on the same problem at the same time. They would slow down. So the solution, obviously, is to go for multiple cores, multiple processors, multiple things all working at the same time. And because of that, I think it's pretty clear that our future is going to become one of writing programs in a multi-core, multi-processor, distributed environment. That's just the way it's going to be. It already is, really, but it's going to become more explicit. So how do we do that? How do we write programs that let us exploit these kind of technologies? Well, it's very difficult. And it's particularly difficult in our current programming languages. Languages such as Java and C# and Ruby. One of the main difficulties we have is how to deal with that concurrency, with 2 or more things happening to the same data at the same time. If you've ever tried writing a concurrent program, a multi-threaded program, you know how hard it is to get it right. When I wrote the first version of the Pickaxe book, I had a chapter on threads. That one chapter had more bug reports than the rest of the book. Right? And they were correct. I had lots of very subtle errors in those programs. And the thing is, all of those programs have been tested. They all ran fine. But they still had bugs that were going to be very, very hard to find. So I think we need to look for technologies that will let us work in this new multi-core environment. And one possibility is to start looking more at functional languages. one of the important aspects of the majority of functional languages is they have something called immutable state. This means that once you've created a data structure, it is never going to change. You can never make a change to an existing data structure. All you can do is copy it and make the change as you copy. And the advantage of this in a multi-core or multi-processor environment is you never have to worry about locking the data. Right? It's never going to get changed underneath you. Instead, you pass the data around effectively using messages, and it just takes care of itself. Your programs can be almost automatically parallel, which is fantastic. And rather than thinking of objects as being the things that hold the state in your program, now we're going to think about processes as being things that transform your data. I think we're going to move from a philosophy of thinking about state to thinking about transformation, which to me feels very natural, because underlying everything I do is transforming data. That's what programming is. So I think that this approach is actually very natural and it's going to work well for us. So I am not saying that the future has to be Elixir, but I am excited by Elixir, and I think it's an interesting example of where we should be going. Personally, I'm using Elixir more and more for my coding. So I just wanted to show you what it looks like. I think Elixir, obviously, is a functional language. It's a concurrent language. I think it's very pragmatic. It's very usable. And most important to me, it's fun. Because if I'm not having fun when I'm programming, then I'm not programming very well. All right? It's a very difficult thing to do, to program. And if you're not enjoying it, then you're going to be, you know, I'm not going to do the best job I can. And if you're not doing that, then you should find another job. You know, you should be enjoying yourself. You only get one life. So I always look for languages that make my life fun. Ruby does that, and Elixir is doing that right now. So what is Elixir? Elixir is a language that runs actually on top of the Erlang virtual machine, Beam. It is the same way that Scala and Clojure run on the JVM, Elixir runs on the Erlang virtual machine. And because of that, it's Beam compatible, which means that it works with all of the existing Erlang functionalities. Now, if you haven't heard of Erlang, it's a language that was first developed for writing software inside telephone switches. High concurrency, high reliability. They talk about getting, depending on how you measure it, 7 or 9 nines reliability on Erlang programs. There are many Erlang programs that started running when they delivered a telephone exchange and have not stopped running since. You can upgrade an Erlang program while it's running. You can change individual components in it. And it has fantastic libraries for managing those kind of large-scale distributed multi-process systems. And because of that, and because of the fact that Elixir runs on top of it, then you get all of that for free in Elixir. So let's just show some of the features of Elixir to show you how it feels to write Elixir code. First of all, Elixir has something called pattern matching. This is going to sound as though it's a little theoretical, but this actually changes the way you think about programming when you use it. Do you remember back at school, you used to write equations that looked like this, right? So the assignment statement here is not an assignment. It's not like a programming assignment. Instead, what this is, it's an assertion. It says that a plus b is equal to 5, and a minus b is equal to 1. It's an assertion. It's not an assignment. Well, Elixir has exactly the same thing. It calls it pattern matching. So this is some valid Elixir code. Some variable equal sign 1, 2, 3, a list. Now you might look at that and say that's an assignment statement, but it's not. In Elixir, it's an assertion. As a programmer, I am telling Elixir that var, the variable, and the list 1, 2, 3 have the same value. And Elixir says, how can I make that true? And it makes that true by binding var to the value 1, 2, 3. So you say, see, I told you that was assignment. It looks just like assignment, but it's more subtle than that. For example, if var is set to 1, 2, 3, then it's also perfectly okay to write that, because it's true. Yeah? It is not okay to write that, because it's not true. So it has pattern matching, which means that it will look to find ways to make the two sides of an equals the same. Pattern matching is recursive. I'm going to show some simple examples here, but it goes very, very deep. For example, if var is set to 1, 2, 3, and then I write that second line, well, what's that second line saying? The second line says, I have a 3-element list, and the first element I'm going to call A, the second element B, the third element C. And I'm asserting that that list has the same value as var. Well, how do we make that true? Well, Elixir says I can make that true if A is 1, B is 2, and C is 3. So that's what it does. So at the end of that, A, B, and C have those values. I can also write this. And Elixir says, well, the 2 matches the 2 in the VAR, and X and Y can be 1 and 3, so again, I can make this match. So it's happy. But if I write that, it says, I can't make this match, because you've told me the second element on the right-hand side is 1, but the second element on the other side is 2. It cannot match. You can do pattern matching on lists. So here, I'm assigning 1, 2, 3, 4, a list, to the variable called list. Now, in Elixir, lists are not the same as arrays. A list in Elixir is actually a genuine list. So it looks a bit like this. Now, if I want to pattern match a list, I can do it the way I showed you before, but if I don't know how long the list is, then there's another technique. I can write this code. So you notice the pattern here. I still have list brackets around it, but I say a head followed by a tail matches the list. And in this case, what that means is that the pattern matches if head is 1 and tail is the list 2, 3, and 4. So this assignment is going to take the head off the list and stick it into the variable head and give me a shorter list in the variable tail. And you may think, but that's really inefficient. But no, it's not, because remember, data is immutable. So this list can never change. So it's okay for that tail variable simply to point to the second element of the existing list. It's a very efficient operation. And after that, head is going to be 1, tail is going to be 2, 3, 4. You can also do pattern matching when you call functions. But I want to talk about that in a slightly different context. In conventional programming, we tell the computer what to do. At least we like to imagine that we're telling the computer what to do. But as you know, that can be very, very difficult, because you have to understand the problem, and then you have to understand how to get the machine to solve the problem. Now, in functional programming, we can do it a little bit differently. In functional programming, we can often code by simply describing the problem. And then the solution can just happen by magic. So, what do I mean by that? Let's have a look at Fibonacci numbers. So, if you go to Wikipedia or somewhere, you'll see a specification that the Fibonacci sequence Fibonacci of 0 is 0, Fibonacci of 1 is 1, and then the Fibonacci of any other number is Fibonacci n minus 1 plus Fibonacci n minus 2. This is the specification of Fibonacci. Okay? It's not an algorithm to solve it, it is the specification. That's the Elixir code that implements that specification. Do you notice a similarity? Yeah. This is actually, interestingly, one function. It's a function called fib with one parameter. All right, in the Elixir terms, that's fib/1. But notice it uses pattern matching on that parameter. So in the first case, I have a function definition for fib if its parameter is 0. And if its parameter is 0, then it simply returns 0. On the second line, I have a definition of fib if its parameter is 1. And if so, it returns 1. Otherwise, it returns fib n minus 1 plus fib n minus 2. It's doing pattern matching just like our assignments did. As a result of that, you can write really large Elixir programs, thousands of lines of code, without ever using a single conditional statement. No if statements, no while statements. You use pattern matching instead. And your code is seriously easier to read because of it. Right? Because your brain doesn't have to sit there and suddenly think about two cases at the same time. It's all just linear. Another example of pattern matching. Say I want to find the length of a list. Well, I can specify that by saying, if the list is empty, then the length is 0. Otherwise, the length of the list is 1 plus the length of the tail of the list. Yeah? So just to prove that, if I say, what's the length of the list 1, 2, 3? Well, that's 1 plus the length of the list 2, 3, which is 1 plus the length of the list 3, which is 1 plus 1 plus 1 plus the length of the empty list. And the length of the empty list is 0. So now we've got the length of our list is 3. So how would I code that? Well, I wouldn't because it's a library function that does it, but to show you the code, it would look like this. Again, it uses pattern matching. So the length of an empty list is 0. Otherwise, the length of a list with a head and a tail is 1 plus the length of the tail. And it turns out that this code is phenomenally fast. It's really surprising that you can have recursive routines like this that actually run in very, very good time. So the other thing that functional programming helps you concentrate on is transforming data. So here's code that you could write in any programming language, in Java, Ruby, whatever else, right? So we create some function that squares a number. We have a list, we sort it, we square that list, and then we output the result. You could write that in anything. Now, quite often, you want to write that in like a more compact form. Oh, actually, before that, sorry. This is just a small optimization. It's Elixir syntax to create an anonymous function that squares its first argument. I could just write that. So to write that, you might be tempted to write your code something like this. So you take the 457 square, etc., etc. The problem with this is that it executes code from the middle out. So it starts by taking the list, then it sorts it, then it does the square, and then finally it outputs the result. And as a result, this is hard to read, and it's also hard to work with. So Elixir came up with a really cool alternative. They call it the pipeline. So here I take my list, I feed it into the sort function, I take the result of the sort function, feed it into the map function, take the result of the map function, and feed it into io.puts. Matt and I were talking about this an hour ago. And I said to him that this changed the way I think about programming. And he said, but it's just method chaining. And I said, no, it's not. When you think about method chaining, you're thinking about methods called, right? You're calling methods to do things. I said, when I write a transformation, I'm thinking of the data and how it undergoes changes as it starts at the input and goes to the output. When I write my code now, I write the top level program as a list of these transformations. Read the input, process it, format it, output it, whatever it might be. And I just write that transformation. And then for each of those lines, I'll go and write the transformations that make that line happen. And in the end, my entire program is automatically written for me just by thinking of transformations. Elixir is very rich. It has, as I said, immutable data. It runs on the Erlang VM, so it has its own process model. We have all of the structuring things you'd expect, except it does not have classes. It's not an object-oriented language. The coolest thing, if you like metaprogramming, is it has a proper macro system. So in Elixir, for example, def, which defines a function, is not actually a keyword, it's a macro. In fact, do, that defines a block, is also not a keyword, it's a macro. So the whole language is soft, which means you can change things if you want to. I don't have much time, so I just want to go through the rest of this fairly quickly. Elixir is concurrent. And that changes the way you think. What if creating and running a new process was as cheap as creating an object in Ruby? Well, in Elixir it actually is. In Elixir, I create processes using spawn. And that creates a process, but it's not an operating system process. It's not even an operating system thread. It's a process that's managed by the Erlang VM. It can be a process that runs on my machine, or I can actually spawn a process that runs on my computer back in Dallas from here. It's all transparent to me. Processes talk by sending each other messages. It's the only way of communicating between processes. So here, for example, I create a function that has some code in it, and I spawn that function. The code uses this arrow operator to send a message to its parent. So the arrow says, send a message. The message it sends is something called a tuple. You can think of that as being like a record in most other programming languages. It's just a fixed arrangement of data. So this tuple is, in this case, it's the process ID of the child and the string, hello from child. So in the main line of code now, that receive block is waiting for a message. This is a pattern match. So in this case, I'm just going to receive whatever the person sends to me. There's no pattern in there. But I could, for example, say, I'm going to match only a message that starts with OK, or only a message that has 3 elements in it, or something like this. And I can have multiple pattern matches, so I can do multiple things depending on the message that comes back. Processes are lightweight. This machine is a kind of like middle-of-the-road MacBook Air. I can run something like 2.5 million processes on it before, no, sorry, 4.5 million processes on it before it starts getting a bit bogged down. So just to show you that, here is some code. It's a bit clever, so you have to forgive me, but what it does is it runs 1 million processes. Each process sends a message to the next process. And that process, the message is a number. And when a process receives that message, it increments the number and sends it to the next process. So here we have, in memory, 1 million processes waiting for something to happen. I now send the last of those processes the number 0. It sends 1 to the next one, it sends 2 to the next one, etc., until at the end I get 1 million. If I run that on this machine, it takes 7.5 seconds to run 1 million processes. There's no concurrency here. Right? If this was a concurrent algorithm, it could do the same work in 2 seconds, because I have 4 calls on this machine. But this is fast. Right? You can think of processes just like being objects. Say, for example, you wanted to write a parallel map function. So it has some data, it wants to transform that data, so it sends each of the elements to a separate process, the processes do the work, and then you combine the results. How would you do that? Well, there are many, many bits of code, but I like to think of it as a transformation. So a parallel map, PMAP, takes a collection and a function. And it takes the collection and transforms it into a set of processes. It then transforms the set of processes into the results. So it's a transformation. So that's the first line of code I would write. I would then have to write the code that implements collection, spawn children, and collect results. So spawn children might look like that. I take the collection, and for each element in the collection, I convert it into a child. Spawn child uses that spawn call that we saw to run the child, and the child runs the function and sends the result back to the parent. Now, if you're not used to Elixir, it kind of looks a little bit funky, but reality is that's very, very simple code. The other side is the collect results. So collect results is given a list of process IDs, and all it does is it waits for data from each of those processes and assembles the result from them. And that's what that map function is doing there. So as a result, now we have a parallel map function. I can run parallel map to calculate, say, the first 50 Fibonacci numbers. If I run it on this machine serially, it may take 2 minutes. If I run it using PMAP, it will take 30 seconds, because I got 4 cores. But it genuinely is that simple to run parallel code. So Elixir is functional, it's concurrent, but it's also distributed. What do I mean by that? Well, Elixir code runs on the Beam virtual machine. So it has these things called nodes, and a node is just an instance of the virtual machine. Each node can run, well, I can run multiple nodes on one machine. I can run different nodes on different machines. And they can all communicate back and forth. So if I have one node and another node, they can spawn and multiple processes between them. If I have a process on node A, I can say, hey, run this process on node B. And automatically messages between them will get sent back and forth. If I have multiple machines, I can run multiple nodes. And again, the communication is just transparent. My parallel map function, with a very small tweak, could run code across all the machines in my office. And that is really, really nice. But there's a problem. You have all of these nodes all processing data. And you could have, in a big application, hundreds, thousands of these separate processes all running, doing things. And one of them dies. What do you do? Well, the OTP system that Erlang, is basically a framework on Erlang, handles a lot of this for you. And in this case, it handles it using a thing called supervision trees. Imagine your processes are organized as a tree. On this diagram, the green circles represent supervisors. These are processes whose whole job it is to monitor child processes. You can write the code for them to do anything you want, but all they do is monitor children. So here's a supervisor, and those are the processes it monitors. Here's another supervisor, another set of processes. And here's a top-level supervisor that ends up monitoring the whole thing. So if I'm a supervisor and a child dies, I have some options. I can restart it. So it just basically picks up. I can restart all of the children if that process dies. Or I can choose to restart that process and any younger processes. This sounds very simple, but it turns out to be the key to creating resilient systems. The trick is to work out what part of your application is important. You'll say, but all the application is important. No, it's not. In particular, the algorithm part is not. It's the data that it works on that's important. Because if the machine that runs some tax calculation crashes, as long as you still have the original data, you can just restart it and rerun the calculation. And that's the way this is organized. So you organize it so that your data is kept in processes that are pretty much never going to crash. They're safe. So you don't put any code in them, apart from the code that lets you get to the data. And then you put all of your processing somewhere else. And if you write your code like that, you can achieve the 9 nines reliability that Erlang claims for its programs. I also say that Elixir is pragmatic. It is, like I say, fully compatible with Erlang and OTP, so you get all of that goodness for free. It comes out of the box with a great build tool, a test framework, documentation system, and also something it borrows from the Python world. You can actually test the documentation in the code. So if you have code examples in your documentation, you will actually run them to make sure that they're correct. It does come with some web frameworks. There's 2 big ones at the moment, one called Dynamo, one called Chicago Boss. But personally, I hope that Elixir does not become another language to write web frameworks in. I would much rather do more interesting things than web frameworks. I think that the future is not the browser. Right? The future is way more distributed and way more granular than browser-based applications. Not tomorrow, but 5 years from now, 10 years from now. Clearly it comes with a compiler. It also has an interpreter version. It has a tool called Mix, which is a bit like Rake for Ruby. It lets you manage a project. It has a test framework. Here's an example of the test framework. A bit like test unit. So I have here a test, where are we? Oh yeah, let's look at that last one. Test count is defaulted if 2 values given. Assert, and then we have a call and the expected result with the double equals between them. Right? So that just looks like a regular assertion in any programming language, right? But if we change that so it fails, notice the error message. Expected user project 4 to be equal to user project 5. It actually works out the values on both sides. How does it do that? Because it overrides the meaning of equals equals, so that it can capture the 2 sides of the expression. And it does that using that meta-programming support I was talking about. But because it's built in, it can do it in such a way that only that one execution of equals equals is overwritten. All the rest are just, you know, the way they were supposed to be. I also say Elixir is fun. Like I said, I think that's really important to me. But I'm not going to convince you that Elixir is fun simply by saying I like it. So I think if you want to try it, download it, and just hack. It's an interesting experience. So Elixir makes me happy just like Ruby makes me happy. And I just would recommend that you should try it. I think we all owe it to ourselves to try new things. And I would recommend this as a thing to try. How are we doing for time? We have maybe, what, 5 minutes for questions? Does that work? Yes. He said 5 minutes. So does anybody have any questions? Oh.
Thank you for great presentation. I tried learn the Elixir, and I understand Elixir language specification. But what Elixir or functional programming language fit for? I think Ruby is almost Ruby used for the Ruby on Rails and web programming. But I don't understand what fit for the what the Elixir fit for.
Right. So what? Yeah. What is the sweet spot for Elixir code? That's a very good question, and the answer is we don't know. Well, okay. So imagine this was 2003, and you said, "What's the sweet spot for Ruby?" Yeah. It was when Rails happened that suddenly everybody said, "Oh, Ruby's the perfect language for web frameworks." So I think the same is true in Elixir. However, I can't make predictions. I think that, well, maybe I hope that. I imagine a future where computing is millions of little small processors and processes talking to each other in a kind of a genuine cloud where things appear and disappear, where new problems arise and are solved all dynamically. Yeah? Where this room would have processors built into it, and our mobile devices would be linking to them to get processing done. Right? Now we're already starting to see that. One of the game consoles, I can't remember which one, can actually use the GPU in your desktop as a spare processor, which is freaky, right? So we're getting there. I think that is where I see the sweet spot for Elixir. Not necessarily as the code that you write the application in, but the code in which you write the layer below, the thing that gives you the glue that lets all of these things talk to each other. That's, I think, where I'd like to see it go.
Thank you. I'm looking for my sweet spot for the Elixir.
Well, please write it. Sir.
I haven't tried by myself the Erlang yet, but and I read somewhere that the Erlang is already a functional programming language. And what's the advantage of the Elixir compared to?
That's a very good question. So Erlang is a perfectly capable language. It is also, to most people's eye, quite an ugly language. It can be hard to use, and it doesn't actually have many of the features that Elixir has. And that sounds strange because they run on the same virtual machine, but think about Java and Scala. Right? Java does not have the functional programming things that Scala has. So Elixir is adding a lot of extra functionality and a lot of extra convenience to, for example, to write a server application in Erlang, the recommended way is to use Emacs and to use Erlang mode, and you type some magic key sequence, and it fills your buffer with about 150 lines of boilerplate code. And then you put your server code into the right places. In Elixir, you don't do that. In Elixir, say, I'm generating a server, and then you just write your own code. Right? There's none of the boilerplate, because the macro system takes care of it for you. So it's not radically different, but it is an order of magnitude more convenient to use. And that makes a big difference when you're programming.
So I don't have to try the Erlang before Elixir?
You certainly can. And I think in the end, it helps to have a little bit of knowledge of Erlang, because you will be using some Erlang libraries, even from Elixir, in the same way that you use Java libraries from Scala. So it's probably doesn't hurt to know a bit. But you can start with just Elixir, definitely. Okay, 1 minute.
The last question.
You have 30 seconds.
This is my this big question for me. Elixir E is, which is correct, large case or small case? Logos E is small. This Elixir E is large.
I don't know. I don't. To be honest with you, I think it's probably small. No, I don't know.
I have the interactive shell open and it's a capital.
Yeah,
Capitalized
that's what,
letter,
yeah.
so I think it's,
And I think the website uses a capital as well. I think
Yeah.
maybe just the logo has a small one because it looks good. I don't know. Sorry.
Thank you.
All right,
May I ask one question?
please.
Why did you take your shoes off?
Why did I take my shoes off? I always take my shoes off when I speak. And it started because I was giving a talk in Norway, and they had a platform, and it was wood on top of some scaffolding. And when you walked across it, it went boom, boom, boom. So I took my shoes off so it would be quiet. So I could walk like that. And I discovered something very funny. And that is, if you take your shoes off and talk, you talk better. I don't know why. you're more grounded, you're in touch with the earth, I don't know. So now I always take my shoes off.
Okay.
But I can also say it's a sign of respect for the hallowed ground of an audience. I don't know.
Okay. Thank you very much.
No, thank you.
Thank you very much, Mr. Thomas.